Carlos Plain, a teacher at Durham School, says, "For sure, I spent my whole life on Earth promoting a certain theory about the universe, and now that theory is being tested, I encourage that because that's how we move forward. That's how we make progress in science." Many of the things that people thought were true in astronomy before the James Webb Space Telescope came along. We have made mistakes in astronomy, as shown by another very deep picture. The telescope, which was meant to show us the most important stars in the sky, is now becoming an enemy of the old view and could teach us a whole new science. Certain experts are excited about the new facts because they have long thought that something was wrong with the old theories. Not all investigators are scared of the new facts. Just the mistake in figuring out how fast the universe is expanding should have made researchers think twice a long time ago, but they stuck to old ideas because everything else was the same. People think that the cosmic microwave background radiation, CMB, is the most steady light in the universe. It was created about 380,000 years after the Big Bang, when the universe was cool enough for electrons and protons to combine to make stable hydrogen particles. Researchers call this time reionization, and it let light into the world. The CMB was first seen by American scientists Arno Penzias and Robert Wilson in 1964. At the time, they were working on a different type of radio receiving wire technology. For a while, this discovery was seen as possibly the most solid proof of the Big Bang theory. Penzias and Wilson won the Nobel Prize and will go down in the history of science as the most important people who ever did it. The CMB probably gives us a look at the hot universe with little change in temperature, telling us important things about what it was like soon after the Big Bang. Scientists use the CMB to get a good idea of the basic assumptions of the material universe. For example, they used it to check how fast the universe was expanding. Edwin Hubble, an astronomer, fixed this problem in the late 1920s by discovering that faraway grand structures move away from us in all directions at the same speed. These things we can see are now called the Hubble rule, or the Hubble constant. When the CMB was found many years later, Hubble didn't have the high-level evaluation tools that were available at the time. This led to a new calculation of the expansion rate that was usually lower than Hubble's original number. Later, scientists figured out the rate again by using Type I supernovae as standard candles. These gave off stable light that could be used as an accurate point of measurement. The tests done in the CMB showed an expansion speed of about 67 kilometers per second per megaparsec. The tests done with supernovae showed an expansion speed of about 74 kilometers per second per megaparsec. What does this condition really tell us about how fast the universe is expanding? Did you know that people have heard about this mistake since the 1990s? Since then, scientists have known or thought that there might be a problem with the way the CMB is being studied, the methods used to evaluate it, or the idea that the universe is expanding. In the field of science, the difference between the different estimated possible gains of the expansion rate is called the SAA tension or Hubble tension. It's very important to note that this stress could damage important parts of our ability to understand the world. For a long time, experts weren't sure what was going on. Since the James Webb Space Telescope started working, it has given scientists amazing data that may now help them figure out how fast the universe is expanding. Some systems are so old and developed that their growth could have started before the Big Bang, which would mean that old ideas about cosmology were wrong. No longer do researchers talk about mistakes or judgment contrasts. They talk about the best crisis in modern stargazing. The rate of growth might not be right, and the idea of progress or the Big Bang itself is being looked at. Pictures put together in different ways show that the world is not at all what we thought it was. The first rebuke came from the SAA. Now, experts who still believe in old ideas have to deal with the question, do we really know a lot about the universe? As different scientists stand on the remains of their beautiful source of both joy and pain, they look into space with fear and try to make sense of what they see. Because science is in trouble, we should think about what we really know about the world. To answer this, we need to understand how science works. To get from the general to the specific, theoretical scientists use a lot of different tools, such as mathematical models, careful data, and rational reasoning. Their understanding is a mix of what they've seen, what they've noticed about others, what they've seen so far, and what they think might happen. The word theory itself makes it clear that these are not facts but rather ideas and concepts. We only have data that we can use, like the pictures that telescopes take, the sound waves and radiation that radio telescopes pick up, and the most current information from systems that measure neutrinos or gravitational waves. With the James Webb Space Telescope, we now have a tool that can separate the purest light into its individual bands and study them in amazing ways. Webb can show us the big parts of world universes that were around more than 13 billion years ago, along with how much mass they held and how many stars were in them. It can also copy the shape and path of a world's progress. Webb may also have flaws. For example, it may not always be able to confirm whether we are seeing universes or black holes with huge gathering rings that shine as brightly as a universe. It's time to face the fact that science has long accepted too many possible results as experiences and allowed for alternative explanations. Research has known for a long time that it is correct. As is generally the case in science, the most recent discoveries from the James Webb Telescope are very important clues to replace hypotheses with new insights. Analysts are generally holding off. The new information is shocking without reason, and different investigators are having a hard time coming up with new reasons. The new information rocks the roots of our science and worries many experts. Many of the examples of real science today are still based on Isaac Newton's work from the 1600s. For many years, his laws of growth and gravity were the basis of our real understanding of the world and the universe. That being said, his ideas about space needed to grow, and Albert Einstein mostly finished up this work near the start of the 20th century. Einstein's amazing theory of relativity, which came out in 1905, shook up the way we thought about reality by showing that things are relative to each other and depend on how good the viewer is. His general theory of relativity, which came out in 1915, added to this idea by using math to show that gravitational quirks do exist. It looked at how masses like stars and worlds can bend space-time. Einstein's ideas and rules were useful in many areas, but he also knew when they stopped being useful. He knew that his theory could never fully explain the universe, and he longed to see a world condition, but he never did. Up until now, no other trained worker has had them step is where? Wouldn't it be cool to know where it is? In a meeting, the famous American astronomer Michio Kaku said that solving this problem would definitely win a Nobel Prize. Allow us to investigate whether the experts may have ruled out possible misunderstandings or whether our binoculars are to blame. The main ideas that people think are causing the cosmological problem are dark matter and dark energy. As our models of the universe get better, they support the idea that dark matter and dark energy make up about 95% of the universe. Either way, neither has been clearly seen, and proof of their appearance has never been shown. They most likely won't exist in any way, shape, or form, which means that the universe's events and the building blocks of frameworks need different answers. On the other hand, they might have qualities we don't know about yet. One idea is that dark matter and dark energy's real qualities have changed over time, which might reveal some kind of truth. Gravity is clearly another plan that should be tried. This power, which can be shown through mass or a bend in spacetime, has not yet been shown. The ideas behind the spacetime curve mostly come from Einstein and are generally accepted. In any case, we can't stop the chance that gravity has traits we didn't expect, or that the long-term pull between objects is caused by something else. In cosmology and stargazing, a few things have been talked about as eternal truths. Looking into the universe has always been a journey shaped by our constant search for knowledge and understanding. From ancient astronomers taking notes on the stars to modern space cameras testing the depths of the universe, this search has always been a journey. Each new development or idea has led to the discovery of new mysteries and the testing of long-held beliefs. In the field of astronomy, the James Webb Space Telescope, JWST, continues to help us make progress. It promises to change how we can figure out how the universe began and how it is expanding. With its huge capabilities, JWST is a big step forward in monitoring space science. It will be able to look deeper into reality than ever before. The CMB is one of the most precise radiations. It is often thought of as the sparkle of the Big Bang and shows how the universe looked just 380,000 years after it first met the world. This old, rare radiation tells us important things about the universe's hidden conditions, like how its temperature changes, which are necessary to understand how worlds and huge structures form and grow. A mistake in the planned possible gains of the Hubble constant, called the Hubble pressure, has been talked about for a long time. It says that there is a problem with the way we think about the world and how it all began. Webb's new finds call into question long-held ideas and make us wonder if our view of how the universe is getting better is too fixed. New ideas might reveal parts of the universe's creation that we haven't seen before. This raises questions about dark matter and dark energy, two things that make up most of reality but can't be explained. Our ability to change our hypotheses based on new knowledge is key to the progress of science. Webb's project is a good example of this. Its findings will help future cosmological discussions and should lead to new ways of thinking about the mysteries of our universe. Cosmology may go through big changes in the future, which could have bigger effects on how we understand the universe, from the Big Bang to the ongoing processes that decide its fate. We might not fully understand the answer to the big cosmic puzzle yet, and Webb's observations could be key to finding new truths that could change the way we think about reality itself.